it's like the Industrial Revolution. This is something that's way, way bigger than and this is someone who's not an AI expert, but someone who knows me very well and is like, what you're doing is changing everything. And that is really the scale that I think we may be on the cusp of.
We've kind of gone over here briefly. Genesis Mission. It's a new initiative led by the Trump administration. Break this down for us. What is Genesis Mission?
That's a great question, Rhett. So the Genesis mission is a national mission that we think will accelerate science, energy, and national security through the use of AI. It is a initiative that will build the world's most powerful platform that will accelerate those areas and drive innovation for the entire country.
And so there's three areas it focuses on: energy, security, and science. But is there anything tangible being built here, or is it just building upon, the initiative to dominate an AI?
No, that's a great question. So yes, so Genesis is really about building this platform, right? This thing that is an interconnected platform across the entire Department of Energy and other agencies that will accelerate research in these particular areas. So uniquely, right, as you would probably expect, there are 17 national labs in the DOE system, and each lab we work together on problems, but we typically, form a team across a few labs, work on a problem, and then go work on another problem. And we don't always reuse the same platforms and the same technology stacks as we move forward. Genesis is about using, we'll say, a common platform for 80% or so of those mission elements and being able to interconnect and reuse those assets across many challenge problems. And so it's that reuse and it's the scale, right, of the entire lab system working together that is unique about Genesis.
So with these three areas of focus, energy, security, and science, you're basically going to be building this interconnected system to use AI to improve performance in each of those areas, right? Am I understanding that correctly?
Performance and make, we'll say, transformational progress, right?
Yes.
This is not meant to be an iterative progress in some of these scientific areas, right? The goal is to make transformational gains, right, across a few key areas.
So on each of those points, like let's start with energy, for example. How will this, having this platform in place help enhance, improve things in the energy sector?
Yeah, that's a great question. So in energy, we're focused on three areas, and we will work on many, but we're focused on three areas currently. One is fusion, so bringing fusion onto the grid. The tagline we use is fusion you can plug into. So fusion that is available, right, to produce electrons on the grid is one goal. A second goal, of course, is the grid itself. How can we, right now, right, getting transmission lines, as we talked about before this part of the call, is difficult, right? There's a lot of permitting. There's a lot of processes that have to be moved around. What can we do to accelerate that process? And also, what can we do to make the grid more responsive to real-time demands? And then the third part, and what is really relevant for us in Idaho, is how can we deliver nuclear much faster and in a safe way? So you can imagine being able to use AI to design a reactor and do the most optimal design. You can imagine being able to use AI to help you on the licensing process. We've already announced some public partnerships on that note, and help you with the operations of that reactor. And so those are three kind of key areas, which I'm happy to dive more deeply into if you'd like, that the laboratory is focused on. And this started, as Addison will tell you, prior to the Genesis mission, but is something that INL is very focused on, is delivering these kind of transformational gains to the nuclear scheduling process.
So those other two areas of focus, security and science, how is Genesis mission going to help improve things in those areas?
Yeah, great question. So let's start with science. So under the science area, there are kind of three focus areas that we're currently talking about. One is about seeing molecules in action. So we want to reveal the chemical and biological processes in real time and learn how those unfold. The second, right, is like really getting full understanding of the universe, all the way from quarks to cosmos. And then the third is quantum, and discovering new quantum algorithms. AI is part of our future, when it comes to where we're going in computing. But quantum, we think, certainly in the middle term is another significant part of that future. And so getting ourselves ready from, we went from classical computing, and today we're in this, what we call GPUs, graphical processing unit, that are enabled by something called a transformer, which basically all that means is it allowed us to take AI models that we had to run in serial. We can only run them on one processor once at a time and run them on many all at once. So that's what you're seeing today, right? Like, how do we get to ChatGPT? How do we get to Claude and all these great tools? We got there because we were able to parallelize the problem. Now, quantum is that next leap, right? That allows us to literally add a third bit to the problem, right? And be able to solve some problems today that are impossible to solve, either with classical computing, GPUs, or any other type of computing. So we're looking at, what would some of those new algorithms be that we could run on those quantum computers? So science is really about building that basic, what we call basic science technology, right? That could then enable all of these things to happen. And then from a national security perspective, we're focused on securing our critical materials pipeline. Many things we use every day require rare earth minerals. We used to have quite a bit of rare earth mineral resources in the US. We still have them, but we don't have access to them. So it's reducing dependence on those foreign supply chains, right? Another part is enabling advanced manufacturing, which I'm going to talk about a little bit more, so I'll hold that. And then the third is about discovering new mission-ready materials that don't necessarily rely on us using, we'll call it rare earths, right? Or things that are hard to acquire. So this could give us new alloys or polymers. And some of those can enable totally new assets. In fact, microreactors, we talked about ALO. I won't talk about them specifically, but I'll say just in general, some of that revolution, right, with these microreactor developers has been about using new materials, new fuels, right, that were discovered, right, through these processes, right? So it's important to think about, as technology evolves, part of that evolution is finding new materials to make those available. But one thing I want to focus on a little bit is advanced manufacturing. So if you think about it today, building a reactor, right, is a relatively complicated process, right? You've got to go through this large design ecosystem. Then you have to source materials through a supply chain, right? You have to qualify those materials, and then you've got to construct the thing. The supply chain, especially for like a new reactor, may be difficult to start at first. So imagine a future where you could advance manufacture. You may have a 3D printer or at least used one before.
Mhm.
So think about a 3D printer, but think about it, this 3D printer maybe using steel and other components. And we have in the lab system at one of our partner labs, Oak Ridge National Laboratory, we have done a lot of advanced manufacturing. Idaho National Laboratory too has some of the most advanced 3D printers for certain activities. And so, anyways, the idea is, can we do that advanced manufacturing using those techniques and then find the error, see how the component was printed and qualify it there. So basically using AI to detect, are there any flaws in the print that we made, if that makes sense. Qualify the components as they're being manufactured and advanced manufactured, right? And then use those components in the reactor. And let's take it a step further and imagine robotic assembly, where now you can assemble those parts, right, through robotics. That last part, is it that, that's how probably the car that you drove here today, right, was probably at least partially robotic assembled. So we know the latter part is possible. And the former part, right, you probably personally have seen how great some of these 3D printers can be. And the tricky part is understanding, what are the flaws that were in that particular print, and is this particular print meeting our quality standards, and being able to do that in real time. And so anyway, so that's kind of where we think advanced manufacturing can help nuclear energy. But of course, that type of technology has broad application for many other things outside of nuclear energy too.
So this is kind of an ongoing initiative, but is there certain milestones that you and your team want to hit by a certain date or anything?
So we're not yet able to disclose our milestones, but what we can talk a little bit is what INL has been doing and what we have done in the past. Let's talk about design. We talked about that a little bit at the beginning. So designing a reactor today, people use computational tools, but ultimately you've probably used Microsoft Word before. I think everyone has, right?
Hmm.
And that is ultimately what the design document typically is for any power plant. It's a series of lots of documents. And you might say, well, that's not a problem. Word's easy to use. It is for a small project. The bigger the project, the more paper, the more words, the harder it is to fully wrap your head around that design, right? And the harder it is to work with hundreds of people who are all trying to change all these Word documents at the same time. So the future state um, looks like we'll call it interconnected web of digital things where you change one thing, and at the very least, the computer warns you about that change. But the idea is to actually automate some of those transfers, right? So that when one format is changed to another, that can be done automatically, and then the human verifies that it's correct. And so let's use a real example. So you have a requirement, you want to be able to design a building, right? We'll just use a general example, an office building. And you want so many offices in that office building. So how would you do that today? If East Idaho News wanted to build a new headquarters, we'll say a 90-story building downtown, right? Then to build that 90-story building, right, you would have, you would say, I need this many offices and I need and I want it to be this many stories, right? And then someone would go off, right? And they would draft you the blueprints for that building. They would build you a 3D model and what's called BIM, building information models, that would show you what that building's going to look like. And then someone would take that 3D model and they would recreate it in another tool that will do a seismic shake for you, right? To make sure is it seismically safe, right? We get small earthquakes in Idaho Falls, right? And we have to make sure that our building is resilient to that. We also got to get soil samples and other things, right? So there's a long process, right, to build a building like that. Imagine a future where you put a prompt in for that building. It generates for you automatically that 3D model. And then it takes that 3D model, and instead of a human having to go off and create the mesh, it automatically creates that mesh, that thing that's going to go into the seismic tool, and analyzes it for you. So that's what I think the future looks like. And it's not removing humans out of the loop, right? Right. You're the designer of that building. You're still in charge and you're still going to look at it and analyzing it. But the way I like to think about it, it gives you like a superpower, right? Because you can do so much more quickly and see what do you really want, right? Maybe instead of a 90-story building, maybe you want a 40-story building that uses a larger footprint because it's cheaper to construct. Or maybe the seismic area, for example, in Manhattan, the seismic area is actually different, and you actually can see that in the building. Some are at different heights than others because the bedrock is at different layers in the Manhattan area. So even in one island, in one city, the differences can be pretty stark, right? And so when you look at these analyses, right, you might change the design of the building, right? I was watching a documentary on the tallest building in the world, and they were talking about how like they thought the building would look like X, and then they did a wind analysis and they completely redesigned the structure to be a different kind of counterclockwise because the wind profile was different than they expected in the area. So there's little things, right, that really affect how you design a building, which think about a power plant as a very complicated building where there is more requirements on how it's going to get constructed. So anyway, so we're
Yeah.
looking at how to do that automation. Any more questions about that's something we have done or we're working on now?
Yeah, gotcha. So this whole program is, in response to a big push by the Trump administration to, dominate in AI. Do you want to give any comment about, I know this isn't something you want to talk extensively about, but what happens if we don't make concerted efforts to enhance our current state with AI?
Yeah, so I'll start with I think America is the world leader in AI right now. When you think of the top AI models, there's benchmarks, right, that look at these things. From a all models perspective, I'm just looking at open source models, right? The United States still leads in those AI models. And so that's an area where we have a lot of strength. I think to answer your question today, we haven't felt the world yet where we are not leading in what is for sure, one of the most important technological changes going on. But I think if we don't lead, right, there are some consequences to that, right? Think about our economy. So no longer leading in science. So that means new discoveries not happening in the U.S., which ultimately means our products, right, have less great technology, and that's something that is very foreign to us, right? Many things in the U.S. Actually still are designed here, right, are innovated here. We innovate the world, and I think we have a reputation for that. When you think of advanced semiconductors, as an example, maybe think of NVIDIA, right, which is the most valuable company right now. And NVIDIA designs their chips in the United States. Now they do manufacturing overseas, but that design happens here. A lot of the equipment for those for those chip manufacturers actually still happens in the United States, the manufacturing of the equipment, or in our or in Europe and other countries that are close to the US. So imagine a world where no longer would that be happening here, right? And imagine all the all the ramifications thereof from an economics perspective. I don't want to go into detail on the national security ramifications, but hopefully people can think about that. But an area that I think is an area that the U.S. needs to think about is energy. We most For the most part, right, we've deployed some new energy assets in the country, but for the most part, we've just gotten more efficient, right? So we think about your washer or dryer at home, right? It's probably more efficient than the one you bought last time, right? Think about those new LED light bulbs that you just installed, right? They're more efficient than the old incandescent light bulbs that we had before, right? And you know that because you touched with the old light bulb. Remember, it was hot, right? I mean, I don't suggest it, but the LED light bulbs, right, use a lot less energy and they release less heat. And so there's less loss, right, to produce that light for that room. And so we've gotten much more efficient over the last generation, but with AI, we need more power. And there is a predictable relationship between, at least right now, between the AI model performance and the compute, and then therefore the energy needed to achieve that AI model performance. And so every iteration of AI, right, uses, traditionally speaking, more power than the last iteration. Now, a question you might ask is, but sometimes they get more efficient, and that's true. So we'll take a model from the last generation, we'll make it more efficient, but then the next generation, we need more compute to get to the next layer of kind of technology, right? So at least for the moment, we are seeing this predictable relationship. And that's why you're seeing very, very large companies, Oracle right now, and the Stargate program, right, investing in very, very large computing deployments. But what we need to think about as a country is we're lagging behind on those energy deployments. And so we need to think about how do we get more energy and do it in a way that is economical, and do it in a way that meets the schedule that these AI developers need, and do it in a way that it satisfies the public. So those are the things that, of course, we are looking very closely at.
Yeah. Uh, I enjoyed your comment earlier about AI helping to design this 90-story building in downtown Idaho Falls. Hypothetical situation, of course, but the ways that AI can help do that faster and better, give you a superpower, if you will, like you said. So just kind of along those same lines, with Genesis Mission, like just in general, like what's on the horizon with AI? There's just a lot of talk about AI right now. There's a lot we don't know. But you've kept using a phrase over and over again, imagine a world where. So what is the next big thing on the horizon in the world of AI?
So for us in Idaho Falls, where we are particularly involved in, right, it is a world where I think the future that we envision for nuclear, right, is one that is much more automated. Humans are still going to be in the loop. Humans are important to be in the loop, right? But a process where we can achieve a lot more with a lot less. Think of the Industrial Revolution is the only analogy I can kind of describe it. So I've of course talked about this at dinner conversations in Idaho Falls, and I used to say, maybe it's like the internet, but I feel like it's more than the internet, but I don't know how to describe it. And someone very close to me said, it's like the Industrial Revolution. This is something that's way, way bigger than, and this is someone who's not an AI expert, but someone who knows me very well and is like, what you're doing is changing everything. And that is really the scale that I think we may be on the cusp of. And if you imagine pre-industrial revolution, right, things were very expensive because they had to be handmade or handcrafted. Maybe there was a little bit of automation, but very little. And we enabled, right, abundancy, right? We had, the shirt I'm wearing, right, was very reasonably priced, right? Whereas before, maybe you'd have one or two shirts. Now you probably have many at home. And so enabling an area of more abundancy for things like energy, for enabling new health milestones. So we talked a little bit about Google had this incredible possible discovery for cancer, right? And maybe a new treatment option. So imagine being able to solve challenges. It's not to say we can guarantee we will be able to solve every problem, but the hope is being able to solve more challenges that right now are out of reach. So that's another area. So abundancy, being able to solve problems that are out of reach, right? And then, of course, keeping the country competitive and being a world leader, which is something we are very accustomed to in the United States, right? Being, I think, hands down, right, the world leader when it comes to science and technology.